I'm Sarah, and I'm here to represent Leticia, who couldn't come. And I will talk about our results on exploring supersolid dynamics in spin-orbit coupled BECs. But I will, I think my animations are not working. I think that's a problem. Okay, because there's things appearing and disappearing. It's going to be very confusing. Yeah, that's better. Okay. So I will start with a bit of advertisement. So we work in ICFO, that is here close to Barcelona, about 10-15 minutes walking to the Mediterranean beach. And this is a picture of our institute. And this is Leticia, our group leader. And in her group, we have 3 experiments. The potassium lab, where we do potassium spin mixtures. Here, multi-component means 2, but the past, present, and future of this experiment is like really, really connected with a lot of the things that we've heard here and with the things that people have done. So I think it fits very well, and I'm really grateful to be here. Besides the potassium lab, we have the strontium lab, which is a strontium quantum gas microscope. And they have recently shown that they can do single atom imaging. They have shown they can do the bosons, but they have recently shown they can also do the fermions. And they can even do SUN spin resolution. So every different color here in this picture corresponds to a different spin of the fermionic strontium. And then there's a third lab, which is currently being constructed, which is our strontium Rydberg tweezer lab, which once it is constructed, will work on a quantum simulation of lattice gauge theories. Okay, but I will talk of the potassium lab, and I will talk of supersolidity. So what is that? When we take the properties of a superfluid, its frictionless flow, and we combine it with the crystalline pattern of a solid, what we get is a supersolid. So that is something that has both the spontaneous U1 symmetry breaking of the phase and the spontaneous translational symmetry breaking. And so these 2 symmetry breakings really have to be spontaneous, so you cannot just put it in an optical lattice. Then you get a supersolid, and the important thing is also that you need to have 2 independent order parameters, and that means you get 2 Goldstone modes, 2 Higgs modes, and more generally you get superfluid and crystal excitations. So this is really an counterintuitive phase of matter with very exotic properties. And as you can see, this has been proposed already in the late 60s, 70s, but in the context of solid helium. But unfortunately, in solid helium was never conclusively observed. But then in the last 10 years came cold atoms to the rescue, and were able to realize systems that are at least similar in some of the properties. So in solid helium, it was like a 3D crystal with like 1 atom per site that was envisioned, and of course the quantum gas systems are a bit different, but still the core properties of this double symmetry breaking and the 2 different properties can be seen here. And one of the systems is cavity supersolids. And in the same year, it was also seen supersolid behavior in a spin-orbit coupled BEC. So this is the platform I will be talking about. And then 2 years later was seen dipolar supersolids with supersolids in dipolar gases. And now the interesting thing is that when we look at the dynamics of these systems, they behave differently. So in cavity supersolids, the period of this crystal is fixed by the light wavelength. We have a rigid crystal. However, in dipolar supersolids, we have a very rich excitation spectrum that has been observed and that hosts phonon modes. So you have a flexible crystal, and of course this is something that you would kind of expect from something that's a solid. You would expect it to host phonon modes. But then the question is, what about spin-orbit coupled BECs? And here the problem was that dynamics was considered inaccessible for a long time, mostly because the modulation that was achieved in these systems was very small. And so it was very hard to observe these systems, and you can see while you have like in situ imaging here in these two systems, these systems here were observed indirectly through Bragg spectroscopy. So it's really hard to tell something about the dynamics. But as I will show you, we have now managed to access the dynamics of these systems, and to spoil already everything, the system can host von Neumann modes. But okay, let's go step by step. I will explain to you how we make spin-orbit coupled BECs in the lab, how we have realized and imaged the supersolid, how we have characterized it, and then most importantly, we have seen a crystal compression mode. Okay, so let's start. We work with bosonic potassium in the lab. We can make BECs both of potassium-41 or of potassium-39. In this project, we have used potassium-41, and we typically work with spin mixtures. So that means here you see the different Zeeman states of potassium, and we work with two different states here, and in this case with the orange and the blue one. And the reason why we pick different states and different isotopes is because potassium has a magic property. It has Feshbach resonances. And by picking a specific isotope and a specific combination of spin states, and then a specific magnetic field, we have really a huge tunability of the scattering properties. So in bosonic mixtures with two components, there's three different scattering lengths: the up-up, the down-down, and the up-down. And we have one tuning parameter, which is the magnetic field. And then in the spin states which we're working with here, for example, at the magnetic field around 50 Gauss, we have these two different scattering lengths. And in this experiment, we sit somewhere in between here, where we can then tune a bit the ratio of the different scattering properties. All right. This property of potassium, of the scattering lengths, was already used in a previous project in the lab, where they realized quantum liquid droplets. We have actually seen this plot already today. So they went to a situation where same spins repel each other, but opposite spins attract each other. And then if you go to a situation where the mean field energy almost cancels and the system is overall slightly attractive, mean field theory predicts that the system will collapse. But if you do the experiment in the lab, you find that it doesn't collapse, and you find these quantum liquid droplets that are stabilized by quantum fluctuations. And so this is great. We love this. We can study beyond mean field effects in the lab. Okay, but now there's a new ingredient in our experiment, and it is Raman coupling. So we take our two spin states, which we label them up and down or red and blue, and we couple them with Raman coupling, a method that was also pioneered by people here in this room. And the trick here is that these two beams of the Raman coupling, they come from different directions. So it could be opposite directions, or it could be under an angle. And then when you go from one spin state to the other, this comes with a momentum kick. Okay, with a momentum kick of 2 kr. And we describe this system by going into the frame where the two bare state dispersion relations, here in blue and red, are separated by this momentum kick. Okay, and what we get is that we have two energy states that are crossing and that are coupled. And this gives us an avoided crossing, and we get new dressed states. So these here. And in this case, we are only interested in the lower dressed state. And what you can see here is that we get now a dispersion relation with a spin texture. So our spin composition continuously varies dependent on momentum. And we can now describe a particle in this dispersion relation as a dressed particle with new renormalized properties. And now we have additional knobs to change the system. For example, we can use a detuning here, and then we get, for example, such a tilted dispersion band, or we can change the strength of the coupling. This means we will avoid this crossing more or less, going from a situation where we follow closely the original bands, and if we couple stronger and stronger, these two minima will move together and will eventually merge into a dispersion relation with a single minimum that looks again very much like a single particle, but with this spin texture and with this new renormalized properties. All right. Also in a previous project of this lab, they went, and Alessio already talked a bit about it, they went into the situation where you have a single minimum here, and you can prepare a dressed BEC here in this minimum. And now if you tune your potassium to a situation where one spin is interacting slightly attractively and the other one is repulsive, then if you kick the system to the left, you will get a soliton, because you have effectively attractive interactions. But if you kick it to the right, you will have repulsive interaction and the system disperses. So you have realized a chiral soliton. And now it turns out, and of course Alessio is the absolute expert here, that when you massage a bit this Hamiltonian, then it fits on the Hamiltonian of this chiral BF theory, which describes an edge of such a quantum Hall system. And from the comic you can see here basically these wave packets which can move in one direction but cannot move in the other direction. Yeah, so that was a simulation of a topological gauge theory. And now to the supersolid. So here we work with the very same system, but in the situation where we have two different minima, which means that in one minimum we have a BEC which is mostly blue spin with some admixture of red spin, and in the other minimum a BEC which is mostly red spin with a bit of admixture of blue spin. But now these two BECs, even though they have different quasi-momentum, they sit in the same position in space. They sit in our optical trap. And since now they are not orthogonal states anymore, they have some overlap in their spin composition, we will get matter wave interference. And this matter wave interference has a spontaneous phase, because it depends on the relative phase of the two BECs, which is a spontaneous property. And we keep the phase coherence of the original BEC, which means actually here we have a supersolid. But now actually Uli explained to us yesterday that if you have two minima in momentum space, then the system will not want to occupy these both minima. And it tends to be energetically favorable to occupy only one. And this indeed is a big problem in realizing spin-orbit coupled supersolids, that one tends to always have this system as a ground state, where of course there's no matter wave interference, and one only has a BEC. And we have solved this problem with potassium, and I will explain how. So we understand this system very much in this language of effective interactions. And now what you see here is on the y-axis the bare state interactions of our system, A up up, A down down, and A up down. And on the x-axis Raman coupling. And what happens is, so in the beginning, A up down is the lowest energy, and it will be energetically favorable to have a mixture with both spin components, and this will be a miscible system. But now, as you increase the Raman coupling, this effective interaction of the left-right will increase. And at some point, when they have a large spin overlap, these two systems, the A left-right interaction will be stronger than the effective A right-right interaction. And at this point, it becomes energetically favorable to sit in only one of the two wells, in this example here in the right-right well. And now you see if these three interactions are very similar, as it is, for example, the case if you use rubidium, this crossing will happen super early. And basically, for most of the Raman coupling strengths, it will be energetically favorable to be in the plane wave phase. And you will only have a very small region with very small Raman coupling, and thus also with very small contrast, because the contrast depends on how much you admix the different spins. And so by using potassium, where we could tune the interactions, we could go to a situation where we have this phase transition relatively late, and where we could go to relatively large contrast. And here you can see our phase diagram, where in the optimal point, we can go up to a contrast of 60%. We work a bit away from this point. We work at zero detuning, just because that is more practical for us. But still we can go to relatively large contrast here. okay, so we can make a stable stripe phase with a high contrast. But the next problem is, how do you image the system? Because this stripe spacing will be on the order of like 1 micron, below 1 micron spacing. So this is really, really hard to image, especially not with single atoms, but with like thousands of atoms per stripe. So what we use is a magnification scheme that was in 2021 published from the Weitenberg group in Hamburg and also already before done by other people. And the idea is basically so we have our system, and it is in one guided trap where we have the supersolid along this direction. And at time 0, we turn off the Raman dressing and we turn on a very deep trap in this direction. And then we will wait for a t-quarter of the trap time. And then we will, by this, map momentum on density and density and momentum. And then after that, we will turn off our trap and we will wait for some expansion time. And again, momentum will be mapped on density and momentum. And through this sequence, we have basically mapped density back on density, but with a magnification. So we have enlarged our system, and this works very nicely. And what you see here is a single experimental shot of our supersolid with the stripes here. And if we integrate along one direction, we get these profiles, which we can now fit and which we can extract a lot of information from. And so the first thing we did is we were looking at the spatial phase, and we see that it's more or less equal for all different phases. Now this does not prove symmetry breaking, because it could be experimental defects, it could be that our system is not stable, but it is a consistency check. And what we also checked is if we increase the Raman coupling, the stripe spacing actually changes. And the black line here is the theoretical prediction, and the gray lines is a double check with time of flight imaging. And why is this happening? Well, as I told you, if we increase the Raman coupling, the two minima will move closer and closer together. This means that they change their distance in momentum space, and of course this changes the spacing of the interference pattern. So as they move closer and closer together in momentum space, we get a larger and larger spacing of the supersolid. This means our supersolid is not fixed by the light wavelength. What we did next is we looked at the breathing of the cloud. So we can excite the system, and then the cloud will change its size in time. And we measured a frequency which is in good agreement with the conventional BEC prediction. And what's actually very interesting is that if we zoom in, for example, here in a small amount of time, we can see as the cloud gets larger, the spacing actually stays the same. So when the cloud gets larger, but the spacing stays the same, you will create new fringes. And this is exactly what we see. So over time, there's more fringes being created, and then later again destroyed again. And this is, of course, something that in a real solid cannot happen. But here we have this superfluid flow between the fringes, and that means that we can dynamically create stripes. And we also looked at the crystal goldstone mode, which is something that has been done already in dipolar supersolids, where you can basically, in a finite system, see how the displacement also comes with an imbalance between the edge fringes. And we checked this in our system, and we find basically a very similar relation between the two, which means that in our system, as in the dipolar system, this finite size goldstone mode of the crystal is excited. And now, most importantly, I want to talk about the crystal compression mode, because there was some misconception previously that it was not clear in the literature whether this would exist in the spin-orbit coupled systems. And actually, already 2021, there was some theory work which predicted quite a rich excitation spectrum, including a stripe compression mode here, but still the challenge was to see it experimentally. But now with our in situ imaging we could, and our data is here. So we basically, we excite the system, and then we wait for some time, and we take images, and we see that depending on time, we really get this very nice oscillation of the spacing. So what do we do? What actually happens is that in the dispersion relation, the two BECs can oscillate. So when we prepare the system, we ramp the coupling faster than adiabatically, and then these two minima start to move together, and they will start, the two BECs will start oscillating in this dispersion relation. And then this gives us an oscillation of the momentum difference in time, and this gives us the difference in spacing. Cool. Now one could ask what happens at the phase transition with this mode, and this is also something we looked at. So as we change the strength of the coupling, we see that this oscillation gets slower and slower, which is something that is expected. We expect this mode to soften at the phase transition. And here the blue points is the frequency of this stripe oscillation mode. And indeed we see that towards the phase transition, it softens, and we see in our data it almost goes to zero. It becomes very hard to fit at some point. And we can also compare this to the dipole mode oscillation, which is basically just an in-phase oscillation of the two components. And we see that this bends down a bit, but it is not strongly affected by the phase transition. And last but not least, we can even tune the phase transition point, because I told you the position of this phase transition depends on the interactions, and we can tune the interactions. So as we tune them, we can see that the phase transition point and this frequency softening of the compression mode starts to happen at larger and larger Raman coupling strength. Yeah, so that is all that I wanted to show you. So in our experiment, we use Raman coupling with tunable interactions. We have seen the supersolid stripe phase with in situ imaging, which has allowed us to characterize the superfluid hydrodynamics of the system, and which has allowed us to see that we have a flexible crystal with a stripe compression mode, and we have a tunable phase transition. I want to thank the team, which is Craig, Ramon, Leticia, of course, Alessio, our theory support, together with Giuseppe, also our theory support, Vasily and Remy. And then new in the team is two members, Ignacio and Andreas. And here is a picture of our combined experiment and theory group. And since there's few minutes left, I will tell you what we want to do in the future. So one very interesting direction would be to combine this spin-orbit coupling with the regime of the quantum liquid droplets. Because with the Raman coupling, we can tune the effective interactions of the system. And that means we could use Raman coupling to go in and out of this liquid phase, and we could basically controllably add quantum fluctuations to the system. And if we go into a regime of the quantum liquid droplets, it is expected that we will see something like a super solid-like liquid, like droplets with super solid-like properties. And a very different direction that we are currently working on, which also Alessio has already mentioned, is that we have implemented a 2D accordion lattice in our system. So this is just a Kapitsa shot where we just flashed the 2D lattice for a very short time on our atoms. And what we can do with this is we can do these synthetic dimensions in a lattice where we get this magnetic flux. And due to the accordion lattice, we can then, so an accordion lattice is a lattice with tunable spacing. And if we can tune the ratio between the Raman recoil and the lattice grid, then that means we can make a tunable artificial magnetic flux. So this is something we want to do. And one of the goals is to see these linear onions that Alessio talked about, and other ideas that also relate to work done by people here is we could try to see this effective magnetic frustration, which the system can map to in the right parameter regime. And with that, I want to thank you for listening.
Questions?
Very nice talk. At some point you say that the breathing mode and the dipolar mode are within this 1.5 ratio. I mean, it's a surprising number. Do you have any physical explanation for that?
So I think the ratio that we expect from superfluid hydrodynamics was something like square root 5/2. And now, I don't remember the number, but if you put that in a calculator, it's consistent with that number.
So for the future, you want to add a lattice. Do you think that, or like a 3D lattice, right, to get the Hubbard? Is that right? Yeah. Do you think that might cause problems with the Raman? Because for Floquet, sometimes it's been like more heating, but maybe the energy scale is separate. I don't know.
It's as if I had paid you to ask that question. So exactly these artificial fields, people do a lot with Floquet. Monica does that, in the Grino group they do that. And the advantage of our system is that we have heating from the Raman coupling, but on the single particle level. So this Floquet, the driving basically is on an energy scale which is similar to the energy scales of the system, the interactions, the tunneling. And so the more particles you put in, the more you start to hit resonances. But for us, we drive between these two Zeeman states, which are like very far away from each other, and this is far away from any resonance of the system. So yeah, we have heating, but it doesn't scale with particle numbers and it doesn't scale with interactions. So yeah, that will be our advantage that we will try to use, that we can make really big interacting systems.
Droplets. How does the density look compared to the droplets? Is it the same kind of high density with three-body losses, or it's much less?
So in these systems, it's like a BC, so it's no high density.
So there's a big difference between that, and you don't have loss problems.
Exactly. So so our heating problem is really off-resonance scattering from these Raman beams, and anything else is on different orders of magnitude.
Great.
In this regime. Of course, if we want to go into the droplet regime, things will look different.
Yeah, same old problems, probably to some degree.
Any more questions? So I have a short one. The fluctuations of these two guys in two valleys, is it phonons? Or, because for me it's a bit strange to think about VCs.
Yes, so I mean, in this, I was a bit confusing about this because I basically said, there's a compression mode, so yay, there's phonons. But what we see here is really a global compression. So it's really like, if we make an infinite system, it would basically be the whole system changing its spacing. And what would, of course, be super nice would be to make a local excitation of this that can then move through the system. But that is experimentally much harder. So we haven't done that.
Okay. So let's thank Sarah again.